Okay, so this method for doing the compositional analysis, I'm just going to give you a kind of a brief run through on how that's done. And what I should do is put out on the course material. Maybe I'll just do it before I forget. There's kind of a nice paper that if you're a little more interested in than what we can get through here. Let's see here. This. There we go. Handouts. Let's see here. That would be there. Okay, it's this paper by Tor Ostad and some other folks, and it's called Practical Aspects of Characterizing Petroleum Fluids, and it talks about the methods of doing compositional analysis. Tor Ostad is he just retired in Trondheim, or in Stavanger, from the university there, and he started Norway's first oil and gas laboratory for the oil industry, and it was a phenomenal lab. It lasted about short of 10 years, and then there was a oil price cratering. It must have been in the late 80s. I don't know my history of oil price craters, but maybe it was right around 90 or something, early 90s. And they had a fantastic oil and gas laboratory running, and price of oil went down to, I think, $10 or so, and then Phillips Petroleum, who was using this lab, in fact, Phillips Petroleum gave the money to the college in Stavanger to build the laboratory, and then they paid back, it wasn't a gift, they paid back the money to Phillips by doing analyses on the Ekofisk fields. And it became a very well-known laboratory, and Tor's a great guy. When that laboratory was shut down, he got into enhanced oil recovery with chemical methods, surfactants, and made a phenomenal career in publications, and he's world-renowned within the field of enhanced oil recovery with chemical methods. He's a fantastic chemist. He's a wonderful person. He's just retired, and he's one of the greats, Norwegian greats in the industry. So anyway, this paper is probably worth if you're interested in more than what I can convey today. It's out there on the website. So basically, what's used is a method called gas chromatography. Has anybody learned about this at the university education? I mean, really learned about it, or you've heard about it? Heard about it, but not really in any detail. I'll give you the Curtis version. I don't really understand what's going on, but I know the people who do, so I won't be too far off. So the thing is that we've got these basically high-pressure samples that we collect, either bottom-hole sample, which is like really high pressure, or separator oil samples, which could be high pressure, anywhere from 10 bar to 100 bar, and separator gas samples, which also would be high pressure. So we basically have this. The problem is that we have pressurized samples that are typically from 10 to 100 to potentially, 1,000 bar is not out of the question, but certainly 500 bar pressure range. And a gas chromatograph, which is basically a device that helps analyze how much methane and how much ethane and how much propane is in a mixture, it won't take such highly pressurized samples. You can't inject these samples in a gas chromatograph. So basically, this is kind of a lower pressure device. And so we can't just send our sample directly into the gas chromatograph, and then Hewlett-Packard, which was the original gas chromatographic company, tells you, oh, you've got 16.2 weight % methane. You can't do it in general. So what we have to do is we have to have a kind of a 3-step procedure in order to get a composition for these pressurized samples. And it's what I call, the first step is to flash. That's step 1. That's to flash the sample down to 1 atmosphere. Okay? And it splits into 2 phases. So you flash the sample down, and you basically get a surface gas and a surface oil. Okay? A certain amount. You can weigh it or volume or whatever. And then these samples, which are atmospheric samples, are then individually, the gas is sent into the chromatograph by itself, and then the oil is sent into the chromatograph. Okay? So we basically send this into a gas chromatograph. We do 2 things with this flashed oil. We send it into a little bit different gas chromatograph, 1 and 2. I don't know. Maybe they're the same kind, but maybe a little bit different. But they're gas chromatographs. In addition, we also take that oil and we measure its molecular weight. We should measure its molecular weight. Okay. So this step here is what I'm going to call step 2. That's gas chromatography. Of surface flashed samples. Okay, that's step 2. So flash, GC, and then in order to find out what what we started with, we have to recombine the methane in the flash gas together with the methane in the flashed oil to find out how much total methane you have, right? So we have to recombine this flash gas and the flashed oil to find out how much methane total was in the sample that we started with, how much ethane, and so forth. So we have to add the amount of the different components in the flash gas together with the amount of those same components in the flashed oil. It's accounting. It's simple. You just have to add them back together. So we call that, or I call this, recombine. Flash, GC analysis, recombine. It's a 3-step process. So every sample from down in the reservoir is done this way, and every separator oil sample is done this way. Okay? So we use this for all bottom hole samples. and that would be MDT type and cased hole as well. And this is the same method that's used for separator oils. Okay. Separator gases in general can be sent directly to the GC. Okay? So the exception to using this three-step procedure is the separator gases. And they go straight to the GC. Okay?
But that's assuming that your separator pressure is atmospheric.
No, not really. I think they, again, I don't know what they do in the lab. When I came to Norway, I didn't have a job. This is another story. I don't have jokes, but this is kind of a true story. So I came to Norway, I didn't have a job. And, but Standing, who I had as a professor, he knew the guy, Øystein Glasse, who was running the PVT lab. So the idea was that I, got here and sold my car. And so I thought, well, I could do something in the lab for Øystein. And, I started doing stuff, and it didn't take, I don't know, too many weeks, maybe a month or so. And all of a sudden, the mercury, they used to use mercury in the labs here. The mercury manometer, which was used to measure pressure or something, all of a sudden, mercury everywhere in the whole room. So, Øystein Glasse was a nice guy, he liked me and stuff. He said, Curtis, you know what we're going to do? We're going to let you do the calculations. Took me out of the lab, gave me an office in the lab area away from the lab. He said, you just stay in here and do all the calculations and we'll be real happy. Everything's good. So that's yeah, again. So I don't really know how they do this in the chromatography part. But it's at, let's say, 100 bar, the gas container. I don't know if they have to put it through a back pressure regulator down to 2 atmospheres and put it in the GC. I'm not sure how they do it. Yes? That's all the other components. Benzene, C6, and on down.
What does it say?
Oh, total, okay, the total amount that was in the sample.
Okay.
Yeah, the total amount. Yeah. Sure, the total amount. We'll get back to this, the detail, but this is, you've got a certain amount of methane in the gas and a certain amount of methane in the oil, and you have to put them back together. Yeah. So I don't know how they do it, but they apparently can take the separator gas one way or another straight into the GC.
No, but I thought you go through flash and then you do the gas and then you recombine just because you might have additional dropouts of liquid, right? But then the gas coming out from the separator is not necessarily at standard conditions.
No, so there are heavier components in the separator gas, but I think, I don't know, but I think, generally speaking, those components will be brought into the GC without fear of losing them. Again, I don't know how it does it.
And what do they do then with the molecular weight of the oil that they measure it?
We'll come back to that. Yeah, we'll come back to that. What we're going to use, why do we do this measurement? We're going to come back to that. I just kind of want to give you the picture of what's done. So they take the sample, they flash it down, they get a flash gas and a flashed oil, put each one through the GC. On the oil, they measure the molecular weight, and then they do some kind of mathematical recombination. That's what they do.
What did the GC exactly do in this case?
That's what we're going to talk about now. Okay. So now, the question is, what is the GC doing? Okay, because I didn't really say. I said it got the amounts of the methane in the gas, amount of the gas. Okay, so how does it do that? What is the methane? What is the gas chromatograph doing? Okay. So again, this is kind of the lab world according to Curtis. which is not right, but it's, so what they do, you got a box, and it's got temperature control, okay? We're controlling temperature in the box, and inside the box, we've got basically a big coil. Really long coil. It's very thin, and it's packed with solid materials, porous material. Okay? I don't know what it's packed with, but it's some kind of solid material. And so what you're doing is you're flowing helium continuously through this chromatograph. And it just flows through because it's a porous material. And then on the outside, there's a detector. God knows what it's doing, but it's detecting something. And it doesn't react to helium. Okay? So the detector, and of course this just, I don't know where this goes, into the atmosphere or something. So the detector, as time goes by, okay, it will give a measure, a detection. If it detects something, it will look like this. It'll look like this. So it's going to go along like this. Nothing's going on. It's just helium. And then what we do is that we inject our sample. Just a small amount. I don't know how big is small, either the gas, the flash gas, or the flash oil. Small amount, a microliter or something. They just inject it together with the helium. So what happens is that, let's say it's the gas, the flash gas. It's got methane, ethane, propane, down to benzene or something. So that goes together with the helium into this column. Those components, methane, ethane, they stick to this material. They stick, absorb, I don't know. It sticks to the material. Helium keeps flowing through. Okay? Doesn't detect anything. But we've got the sample inside sticking to the column. Now we crank up the temperature. Whoa. Okay. At this point we start cranking up the temperature. So now time, so temperature is just room temperature, and we start ramping up slowly the temperature like that. Okay? We just continuously increase the temperature in our box. So what happens is that when you reach right here, that temperature is above the vapor pressure of methane, or the temperature required to release the methane from the packing material, and it joins helium as a gas out the column. So now you've got, at this point, you've got the helium flowing, and all the methane that attached itself, stuck to the column, is now flowing with the helium. And when it comes out, the detector says, gotcha. Okay? And it says, I've got this much reaction, and that's our methane. Okay? And there's a bunch of it in the separator gas, right? Had we injected the separator oil, there wouldn't be a very big area because there's not much methane left in the oil, right? But this is what it looks like. So it detects it, and it's over a period of time, temperature, that it gets all of the methane is out. And the area under this curve, okay, the area is proportional with the mass of that methane. Okay? And then as the temperature keeps rising, ethane pops up. Okay? And its amount is proportional to that area. Propane shows up. Isobutane, normal butane, isobutane, normal butane. And then you start getting all these isomers. And then it'll start going like that. Okay? So you got your C3, C4s, C5s, and then you get a bunch of these C6 and heaviers. Benzene's in there a little bit, normal hexane, normal heptane, and they're all in there. And then you can try to slice these, and what these computer programs do, they slice these because they know exactly in a certain temperature range benzene leaves. Okay? So it knows when the peak of benzene is known. Don't ask me how. They know. Hewlett and Packard are doing this for a long time. Okay? So we get, so maybe this peak here is benzene. Okay? So they get all these things, and they got the areas. And the total area, basically you've got the mass, you've got the area of methane, and if the mass fraction, that's not mass fraction, that's mass. The mass fraction, which we call weight fraction, is just the area of that particular component over the total area. Okay? That's the total area under the curve. And since we're analyzing the gas, this will provide, I'll label it, the weight fractions in the flash gas of component I. All right? The weight fraction of the flash gas in the component I. Any questions? That's what this gas chromatograph does. I don't know how. It's like magic. Okay? And that's because the temperature that's increasing, it basically vaporizes, deattaches the compound that was stuck to the material, and it flows together with the helium out. Okay? That's what happens. Now, when we do it with I'll do it in green here. I'm not sure why, but we do it in green. Now we're going to do the flashed oil. Okay? Yes? Yeah, this is response. I don't know. The detector response. I don't know. They zap it with electricity. I don't know what it is. It's some detection of anything but helium.
And like for the this pressure, the response will get to 0?
Because if there's nothing there, the response, it'll go to 0 because nothing else is coming out except helium. So it's detecting a response to hydrocarbons. I don't know.
There is a definite total area for this curve,
There's a definite total area for the curve, yeah.
not indefinite. Right?
No, not for gas. Not for gas. Yeah. I think if you go to high enough temperature, what may happen is that this thing will actually start growing like this. And the reason it does that is because you're like burning this like column, this packing material. It has stuff on it that dislodges. It's got something, and it goes with the helium out. It gets detected as if it was hydrocarbon, but it's not. Okay, it's something else. So this out here, this is a false. This is kind of this is stuff
So you're burning the
from the column itself. So it's not from the sample we put in. It's from the column. It's made of something, and you heat it high enough, some of those things are going to dislodge and go with the helium. And the detector is going to think it's something. Well, it is something, but it's not what we want. But we generally, for gas samples, we don't see this. Okay.
And in the PVD reports, they report the air fraction in the gas sample.
Air?
Air content.
I don't know. That's the non-hydrocarbon content. They actually do a different tool. If you read that paper, they use a different kind of GC for the nitrogen and the CO2 and the H2S. It's a little different method. It's a gas chromatograph, but it's a different kind of process. I think they call it a flaming ion detector. Flaming ion, I don't know. Anyway, details. So for the flashed oil, we're gonna get a response. Let's say the temperature profile looks the same. So for the flashed oil, you're going to get just a little bit of methane, because not much methane stays in the oil at 1 atmosphere. Okay? You probably even get more ethane than methane. Okay, I'm going to do my best to and then this thing's going to start looking like this. You're going to see peaks, but there's so many damn isomers that they all kind of run together. Okay? So this thing is going to look kind of like this, and it just starts looking like a line. Okay. This may be C10, C20, and you're out to C30 plus or something, or C30. Okay. And you still got stuff coming out. But then you stop. You're done.
Doesn't reach to zero.
No, it never reaches zero because you got a bunch of stuff that's C30 and heavier. It's just left in there. Okay. Now, if you had run at the same temperature with no sample, just helium, okay? Just helium, but at the same temperature ramping. What you would get is you'd get this same line that under here. You'd get a line that went like this. Okay, so this is basically no sample. Okay? Which means that C20 is the area here. Not from the zero, but from where this, we want to take away the other stuff. It thinks it's C20. Okay? So this is called no sample. It's called a baseline. The problem is that baseline you see is increasing. The amount of the C30 is getting pretty damn small. So the C30 amount is that. Had you not corrected for the baseline, you would have thought there's 2 or 3 times as much. So you see the uncertainty is starting to become big. The heavier the component, the less there is of it, but the bigger this baseline shift is changing. Okay? And then we stop. Let's just say we stop here. We have no idea how much of the C30 plus stuff is there, C31 plus. We don't know. Because we don't know the area. So it doesn't help us knowing only the area up to C30. So what they do before they put the oil sample into the container, it's actually a syringe, it's like a needle. This sample is actually our surface oil plus maybe 5%, I'm not sure how much it is, maybe 5% by weight, of some strange hydrocarbon. Okay? I'm just going to call it X. It's some strange hydrocarbon that you should not find in the oil. Let's make it, what color do you want to make it? Pink? Okay. So we know the mass fraction, 5%, in our little sample that we inject into the container. And what happens is that that strange X compound, which is here, we get the area of X, right? And we know that it's physically, we measured 5%. So the total, the AX, which we measure from the GC, divided by the total area, which we don't know, right? That's 5%. So now what do we know?
Baseline.
We know the total area. We got 0.05. We measure this from the GC. We don't know A of T. So that internal standard gives us the total area. Then we use that for all the other components. It's called an internal standard. Okay. So that if we want to look at C10, the weight fraction for C10 is the area of C10 over that back calculated total area. Okay. Yeah.
So this 5% X,
It's physically measured. We make up a sample.
so we add it in there.
That's right. We've got it on the weight. It's 3.682 grams of flashed oil. We add so many fractions of a gram of X, and then we know that it's that much. Yeah, exactly. So we physically measure that, make it up.
Is the baseline similar to the one above?
Man, you're asking questions. I could tell you something, but I wouldn't believe it myself. I don't know. I don't know if they use a different column for gases and oils. I should know, but I don't. Like I said, they wouldn't let me in the lab here. They won't let me in the lab on the 5th floor either. So.
What is the reason of this baseline show?
Because you're going to high temperatures, and the material inside the column is made up of probably some organic stuff, and it just starts dislodging. You know, the helium, the hot helium, brings some of it with it. So it's reacting. The detector is actually detecting something, but it's not what we put in as a sample. So. You know, if we could call Tor on the phone, you know, and Skype him, he would tell you all sorts of. We would never finish because he knows so much stuff. So. Okay. So this gives us this gave us the weight fraction here for this flash gas. Here we've got the weight fraction for the flashed oil. Okay. And then when they do the flash. When they do the flash, they actually get the volume of this gas and they get the volume of this oil. They actually might measure the mass of that flashed oil and its density to get the volume. Okay? Because there's not very much of it, so they have to weigh it, measure its density, and so they get basically the volume. And now the ratio of these two numbers is what we call our gas-oil ratio, flash gas-oil ratio. So what's done is that you get from this flash gas-oil ratio, you can basically get the mass of the gas and the mass of the oil by calculation. And then because we know the composition of this, we know all the components and their molecular weights, we can calculate the moles that became gas. And here we know the weight fractions of all these components. We have to estimate the molecular weights here. And then we can convert this to mole fraction and number of moles. But we have to know the molecular weight of each compound. And what do we not know? We don't know the molecular weight of each compound. What we do know, however, is the overall molecular weight of that oil. That's why we measured it. And that molecular weight, which is measured in the lab, that needs to be equal to basically the sum of the mass, which is the sum of these weight fractions. Of course, that sums to 1, okay, divided by the weight fractions divide by molecular weights, okay, for all the components. That's the moles. These are measured in the lab. These we have to estimate. Okay? This is measured in the lab. So this is kind of a big uncertainty that you have to live with. We don't know what those molecular weights of all the components should be.
So do we measure this molecular weight for every component or?
Just the total. So all you have is this kind of, you have kind of a check. Whatever set of molecular weights you put in there needs to converge this material balance. Yeah.
Is that how they're going to estimate the C n plus
You-
heavy molecular weight?
Yeah, so what some labs do, so some labs, they say that for I equals C6 out to C n minus 1, they use like table 5.2. That's the Katsfiris-Zabadi table. It's some average oil. Some labs used to use normal paraffins. That's wrong, for sure. Okay? Maybe in India it's okay, but it's probably wrong. Most places. Or they use something else. Other estimate. Okay? If you make some kind of assumption here, you can force this equation by just what's the molecular weight of Cn plus, right? You can back calculate molecular weight of Cn plus. So you can back calculate the problem is if you use Katsfiris-Zabadi 5.2 in India, where it should be something more like normal paraffins, the C31 plus molecular weight's going to be crazy. It's going to be like ridiculously high or low. I don't know. Okay? So when the labs, I think it was back in the 90s, tried to do this, they got these crazy numbers. They give a number of 3,280 for, C25 plus molecular weight. Numbers that were clearly wrong. So they stopped doing that. Okay? What they do today, we're not quite sure. We're not quite sure. And I think every lab does it a little bit differently. So this is basically not used much or at all. The point is that you don't really know all these molecular weights. So the conversion from mass fractions to mole fractions is uncertain because we don't know the molecular weights. The amounts of the heaviest, the mass amounts, because of this baseline shift thing, is uncertain. So that for the heaviest, so the weight fractions for the maybe I greater than C25, C20, is very uncertain because of this. We really don't know what the baseline shift should look like. We should, but we don't really know. So there's a lot of uncertainty in the amounts of these heaviest. We certainly don't know the molecular weight. So you can start asking the question, so why the hell do they make the measurements? Okay, and it's a very good question. Okay, but if you just don't worry about it and don't think about it, you get these, this detailed analysis with 4 significant digits or 5, and you feel like you're getting something for the money you paid the laboratory. In reality, you're probably getting a lot of so-so data, not trustworthy data. Anyway, at the end of the day, we make this assumption, and then we finally do the recombination, and that's done. I'll show you how that's done. So you've got, this is very simple. These are from the lab. Let's see, we want moles. So we know these. For the gas components, these are okay. So this is basically moles divided by the sum of all of those. Okay, so this is accurate. We know the mole fractions of this flash gas. This should not be I, this should be like J. I know, it's getting so small to read, I can't. Okay. We do the same exact equation for oil. It's just that there's a bigger uncertainty here. These are okay. The labs will usually just give you these numbers. They'll give you these, probably, maybe not even those. And then the total sample composition that we started with, the total sample composition, that could be ZI if it's a reservoir fluid. Let's just assume that it's some reservoir fluid. Is equal to the mole fraction, that's gas, plus 1 minus the mole fraction, that's oil. Okay, like that. And this FG is from the gas-oil ratio. Okay. That's going to be 1 over 1 plus QR density, flashed oil, molecular weight, flashed oil. That's the equation. So you've got the gas oil ratio, cubic meters per cubic meters, cc's per cc, whatever. Then we've got the density of the flashed oil and the molecular weight of the flashed oil. I think this is right. And then you also need, you need R, TSC, TSC. So if it's SI units, that's like 23.68 or something. Standard cubic meters per kilogram mole. That's what we were looking for. And you can see there's a lot of steps. There's a lot of potential errors to get there. So if they report 52.3681 mole percent methane, they're doing a trump on you. Y'all didn't get that. They're doing a trump on you, saying one thing and not really truthful, but it sounds good. It looks good with 6 significant digits, but it's not really got more than probably 3, at the most 4. That's probably right. This is certainly not right. So if the lab gives you all these numbers, this, if it was honest, that would say plus or minus 0.5 to as much as 2 mole percent for methane. That's probably the uncertainty in reality. And for methane. And also for the total C7 and heavier is probably that. Overall, the total is probably not more accurate than that. So, compositional analysis. You take the sample, you flash it, measure the amounts of the two, do GC on each one, convert to mole fractions, figure out how much moles of gas and oil you had, recombine them, and you got the composition. Okay?